Okay, the mic is on. Okay, I have confirmation it's streaming with the audio, so we can now get started. Okay. So with this class, the last topic that we talked about on Monday was the subtractor, and we pretty much finished the entire topic for the subtractor on Monday. We also went back and looked at the carry ripple adder. I finished most of it. I didn't quite finish the entire thing. I think I did, when I went to the lab. Did I send that file out to you guys, or did I forget to do it? I did not send the file. Okay, so I probably still have it then. Depends on whether I had to reboot the computer in between. Let's see. Yeah, I still have it here. So this is the finished, full adder. I just, put in a bunch of pins and hooked up the wires. This is how it looks like, as a carry ripple adder, which you can see how the carry out from bit 0 becomes carry in of bit 1, carry out of bit 1 becomes carry in of bit 2, and carry out of bit 2 becomes its own pin, which is K3 in this case. I labeled all of the other pins. I should have labeled this one as K3, but all of the other pins are already labeled. You can test it. Okay, so let's go ahead and just give it a test run and see whether it works, or at least whether it works in a simple sense. If I just say 0, 0, 1 plus 0, 0, 0, obviously the answer is 0, 0, 1. If I have 0, 0, 0, 1 plus 0, 0, 1, the result is 0, 1, 0 with no overall carry, so that works. If I have both of the most significant bits turned on, I'm going to have a carry to the overall carry, like so. So far it's working. So I'm just hand testing this a little bit to make sure that it does work. But from what I can tell, it's working. How many test cases do we have as a total to make sure that this design does work in all cases? You look at the number of input pins. There are 7 of them. So that means we have 2 to the power of 7, which is 128 unique test cases. Is that okay? I'm not sure whether I want to talk about it today, but at some point of this class, I'll give you guys a mechanism so you can actually test possible cases, all possible cases, or at least have it logged to an output file. And once things are logged to an output file, you can have another script or program to process that output file and double check and make sure that everything looks good. Okay. So do we have any other questions about adding or subtracting or binary representation of numbers before we move on to signed number representation? No questions? So we are all good? Okay. All right. So in that case, we're gonna. Oh, let me save this file first, and then I'll send it to you. It's already saved. I just have to find out exactly where I saved it. Okay, it's under the temp folder. Okay. And then I'll send it out. Okay. I'm sending it as an announcement, which means you will receive it as an email from your apps account. So this is the carry ripple adder. Let's see, attached. Excuse me. And it is here. There we go. There you go. Okay, so now you have the carry ripple adder. So today's lab is basically just to finish the carry look ahead adder. So make sure that you don't make use of K1 in K2 and make use of K2 in K3, because that would have defeated the entire purpose of having the carry look ahead adder. Okay, so you want to use the most expanded expression for each k term so that you have all the logic spread out, but making it as parallel as possible. Okay, so that's one thing that I have observed, not only from this class, but also from the other class, that people kind of wanted to use the simpler form, but that would defeat the whole purpose of a carry look ahead mechanism. All right, so with this out of the way, we are going to move on to signed number representation, which is right here, signed value representation. Okay. All right. So in here, the first paragraph or the first section, just kind of talks about the general notation that we use when we want to represent something that is negative. So when we look at this particular representation, we know that it is representing negative 45, which is basically saying 45 units to the left-hand side of 0 on a number line. Is that okay? So I don't think we need to talk about this too much. But it becomes kind of a problem when we need to store negative values in a computer, because on a computer we don't have this negation symbol to basically say, oh, what is following is the magnitude to the negative side. So we don't have a negation symbol because all we have are zeros and ones. Is the voltage high or is the voltage low? That's all we get as a physical state. So now the question is, then how do we store values that are negative? So one way that people think and go like, well, can't we do it this way? Okay, so let me show you what it looks like, and then we'll talk about some disadvantages of that approach. I'm looking for my notepad, which is right here. Okay, very good. Okay, so we'll take a look at this particular approach. Let's say we want to store -5 as a 4-bit number. Okay, 0101 as a base 2 number represents what we know as 5 in base 10. Okay, so why don't we use the most significant bit? If it is a 1, it means whatever following is the magnitude, but it's going to the negative side. So this is one proposed method to encode the value of -5. Okay, it looks pretty simple. Okay, we're only using 1 bit to represent whatever the quantity of the other bits is representing is going to the right hand side of the number line or the left hand side of the number line. Seems pretty simple. Okay, but the problem is with this representation, if we want to add or subtract with numbers that can go negative, we can't use the same adder or the subtractor anymore. We just cannot. Okay, in other words, if you add these two, what do you get? Do you get 0 back? Okay, so let's check it. 0101 in base 2 plus 1101 in base 2. And just like with my Tuesday, Thursday class, I'm going to carry out this addition the long way, but I'm not going to refer to any arithmetic operations. What I would do instead, I would say 1, 1. What is the exclusive OR between those two? Is a 0. What about 1 and 1? It's a 1. So we know there is a carry over here. 0 exclusive OR with 0 is a 0. So over here, I can say 0 exclusive OR 0 is 0. 1 exclusive OR 1 is 0. 0 exclusive OR with 1 is 1. Now, when we look at the carry over here, then we have to ask 2 questions. 0 and 0 is 0. 0 and 1 is also 0. 0 or 0 is 0. Is that okay? And then when we look at this carry bit, we have to ask the question, what is 1 or 1? It's a 1. What is 0 or 0? It's a 0. 1 or 0 is a 1. In other words, I am not using the concepts of addition or carrying. I'm only using concepts of Boolean operations now. In other words, I'm emulating an adder, okay, using only logic gates. Now, the way I'm doing it right now is carry ripple because, manually speaking, it is not easy for me to keep track of the complex equation of K3. Okay, if I can do it, it's great, but I cannot. So this is actually a carry ripple method. Okay, so we have one more carry bit here, which is based on 0 and 1 is a 0, 1 and 1 is a 1, 0 or 1 is a 1. So we have an overall carry of 1, which is useless as far as this exercise is concerned. And then we want to compute all the sum bits. 0 exclusive or with 1 is 1. 0 exclusive or with 0 is 0. 1 exclusive or with 1 is a 0. Okay. This is not 0. Huh? It's one way to look at it is 2, yes, but it is definitely not 0. So I cannot just use our adder the way they are designed right now to perform this calculation because the representation of 5 and the representation of -5, they don't really work out in a way that we can use the existing adder to perform computations. So are we okay? I mean, do we understand why this is not a good way to represent signed values? Okay, very good. So then the question is, well, if this is not a good way to do it, how are we supposed to do it? So that's kind of a question that we need to answer. But before we answer that question, one thing I want to do is to introduce the concept of a number circle as opposed to the concept of a number line. Okay, let me go to Zernal, and we're going to open a new page here. So here is a number circle instead of a number line. This is 0. Okay, so we'll try to fill in all the slots in 2 different ways. The first way is let's just continue to move clockwise, okay, and assign interpretations to the bits. So before we go any further, it is important for me to divide this whole thing into 16 or have 16 ticks on the circle, okay, because we're dealing with 4 bits in this case. So this gives me 8. This will give me 16. Okay. So now we want to look at all the bit patterns. Okay, we start with 0. Would anyone argue and say, no, I don't think 0, 0, 0, 0 in base 2 is a good way to represent the quantity of 0? Does anyone want to argue? Okay, I thought so. This seems to be pretty natural, right? Then we have 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1. Okay, I need to lay it a little bit flatter because otherwise my hand is hanging. It doesn't work out that way. 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Okay, so do we have any questions about how I label each tick or each mark on the circle using a binary representation? No? Okay. So unlike a number line, this thing is a circle. In other words, all we have are 16 values. It kind of makes sense, right? Because if you only have 4 bits, you really only have 16 unique combinations of zeros and ones. So if we are using 4 bits to represent values, then you only have 16 unique values that you can represent. Is that okay? Okay. So the first way we look at this is, we'll just assign, when we go clockwise, we're incrementing the value. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, that's one way to assign values or interpretations to the bit patterns. Now remember, even the black, the numbers, they are only interpretations of the bits. We don't really know what the meaning is for 1001. Perhaps it means a pixel should be on, the next one is off, the next one is off, and then the next one is on, right? How many people know what a dot matrix printer is? From way back when. Okay. Anyone who has worked for O'Reilly, like automotive, supply chain, recently, would also know what a dot matrix printer is, because for whatever strange reason they used dot matrix printers up to what, last year or year before last? Until I guess they cannot find replacement parts anymore. Okay, so, but in the case of a dot matrix printer, it is basically saying, yes, we want a dot, we don't want a dot, we don't want a dot, we want a dot. That's kind of, so the print head is oriented this way, and then they have a mechanism, a belt, to move the print head this way, and then it will feed the print head, binary bit patterns like this in order to control whether to have a pin to punch through a ink, how do you call that thing? Ribbon, in order to leave a mark on the piece of paper. Okay, so 1001 may have no particular meaning other than, yes, we want to punch, not punch, not punch, and punch. Okay, so all of these things are really just interpretations. Is that okay? All right, so now we look at this number line and go like, let's take a look at this number line in a slightly different way. Okay, I'm using this only to kind of block out one portion of the screen. So when you're only looking at this top portion of the number circle, it looks like a line again because the curvature is small, right? So it's just kind of like okay. As far as I know, we are living on a planet which is a ball. Okay. Some people believe that the Earth is flat, okay? But I think there's sufficient evidence for me to convince me that no, the Earth is a ball, okay? It's a sphere, okay? But right now, do I feel that I'm living on or standing on the sphere? No, this is flat enough that I can see how some people think the Earth is flat. Same thing here. Okay, so at this point, it looks like, hey, it looks kind of like a number line. Well, if this were a number line, okay, meaning that it stretches to both sides indefinitely, how would you label this particular tick? Seems to make sense that that would be -1, right? Okay, remember, it's just an interpretation. We are assigning interpretations to each bit pattern. So I'm going to use a different color here and say, hey, this thing can also be known as -1. This thing then can also be known as -2, -3, -4, -5, -6, -7, and -8. And I'm going to stop here. I'll explain why I stop right here later on, but we'll just keep it the way it is right now. Do we have any questions about how I assigned interpretations to each binary bit pattern? Are we good so far? So a very natural question is, if there's a particular storage device, somewhere in the computer, and it has 1, 0, 1, 1, what is it really representing? Is it representing -5, or is it representing 11? I mean, it's only natural that we have that question, right? My answer to that question is, what do you care? What do you care? If you're not doing anything with the bit pattern 1, 0, 1, 1, it can be whatever, right? You don't need to interpret it. You don't need to interpret until you have to. Does that make sense? So if we store 1011 somewhere in the memory of a computer, you don't need to ask, what is it representing? I don't know. I don't care. Okay? It is just 1011. Are we good? When do you need to care? when you compare. Yep, go ahead.
Well, I was going to say it's being used as
When you're, okay, so when you, so there are several ways to use a bit, and we talked about an adder and a subtractor, right? So when you add and subtract, you seem to have to know what it is. But I will tell you, the way we make our adder and our subtractor, you don't need to know either. You go like, really? We don't need to know? Okay, let's test this, right? We'll test it with several things. So what we'll do is we'll test, okay, let's check out what happens when I add 2 to 1011. Okay? So on the side here, I'm going to carry out the math. Yep.
So do you add it and then you interpret it?
Exactly. And then see if it makes sense, right? Okay. So we'll go through this addition and we say here is 1011 in base 2, and we want to add 2 to it. Well, how do we represent 2? 0010. Very good. Okay, so we have 0010 here. And I'm going to do the same thing as last time, just so that you guys get another practice of how to use Boolean operations in addition. So 1 exclusive OR with 0 is 1. 1 exclusive OR with 1 is 0. 0 exclusive OR with 0 is 0. 1 exclusive OR with 0 is 1. Can you guys see the cursor? When my pen is just hovering? Just barely, right? There's a small dot that moves. Okay. Okay, that's good. This is an implicit 0 here. So now we need to deal with the carries. This carry here depends on 1 and 0 is a 0. 1 and 0 is a 0. This 0 or this 0 is a 0. 1 and 1 is a 1. 0 and 0 is a 0. This 1 or this 0 is a 1. 0 and 0 is a 0. 0 and 1 is a 0. 0 and 0 is a 0. 1 and 0 is a 0. 1 and 0 is a 0. This 0 or this 0 is also a 0. So we have an overall carry of 0 in this case. Now we get to the sum, which is the bottom line. We have 1 exclusive OR with 0, which is a 1. 0 exclusive OR with 0 is a 0. 0 exclusive OR with 1 is a 1. 1 exclusive OR with 0 is a 1. So we have 1, 1, 0, 1 as a result. Okay. Does it make sense? Right? So if we choose to look at things as signed, which means it can be positive or negative, then 1011 would represent the value of negative 5. The result that we get, 1101, would also represent the value of negative 3. Does it make sense? Negative 3 plus 2 is negative 3. Negative 5 plus 2 is negative 3. Yeah, works out. Yep.
Would you need a subtractor then?
Hmm?
If we can interpret numbers, would we ever need to subtract them?
If you know how to negate a number, then you would not need a subtractor. You're correct. So you can negate a value first, and then you can just use addition instead of subtraction.
Is it more efficient to use a subtractor? Like would our computers use a subtractor?
What do you think? Remember last time we talked about how a subtractor is not that much different from an adder, right?
Right.
I can use one bit to control the mechanism to see whether it is adding or subtracting. So the answer to that question is an adder and a subtractor are nearly equal in terms of how fast they work.
So it'd be a little faster because you wouldn't have to interpret.
Exactly. Okay, so what about the unsigned representation, which means we're only concerned about values that are not negative? In that case, 1011 represents 11, 1101 represents 13. Well, if you add 2 to 11, do you get 13? It all works out. Cool. Well, not so cool, because then when does it matter, right? We can use the same, so whether you want to interpret a bit pattern as signed or unsigned, we can use the same adder, we can use the same subtractor. So now the question is, then when does it matter? Because it doesn't seem like this whole discussion is going anywhere. When does it matter? When you compare. Okay? In other words, when you compare, you're asking this question. Okay? One number is represented as 1011 in base 2. The other number, let's just say 0010 in base 2. The question is the first less than the second? Now you have a problem, right? Because if you choose to interpret 1011 as a unsigned number, then 1011 would represent 11 as a value. And 0010 is always 2, okay? So in that case, the less than would be false. The comparison would have given you a result of false. On the other hand, if you choose to interpret all the bit patterns as signed values, then 1011 would have been interpreted as -5. And 0010 would still be interpreted as 2. -5 is less than 2. The comparison would have given you a result of true. That is when it matters. Is that okay? So for the rest of this class, sometimes you have to undo what you have learned in C and C++. Because when you are writing a program in C and C++, when do you indicate whether something is signed or not? When you declare the variable. Okay, so you say int x, then it is signed. When you say unsigned x, then it is unsigned, right? So later on, if you do comparison, the compiler already knows what type it is, and it would use the correct interpretation. Is that okay? But in assembly language programming, and also at a very low level inside the computer, when you store, it doesn't care. When you add, it doesn't care. When you subtract, it doesn't care. It is only when you compare, then you have to say, okay, how do we differentiate between the signed comparison versus the unsigned comparison? That is the only time you need to know how am I supposed to interpret the bit pattern. We'll get to that. It has to do with other flags that we keep track of when we perform subtraction. So subtraction is the basis of comparison, but because we have certain flags other than the borrow flag that we have not talked about at this point, so I can't really tell you exactly what the difference is, but we will get to that, okay? So right now our focus is just, do we know how to represent a negative integer given a certain number of bits? That's our current issue. Are we doing okay so far? Yes? Okay. So when you look at this number wheel, it also tells you the range of values that we can represent, right? So if you choose to say, I only care about non-negative values, then the maximum value you can represent is 15. Are we good? The minimum is really trivial because the minimum non-negative value is 0. Okay, so that part is pretty easy. But if you choose to say, but I want to store or interpret both positive and negative values, then you have to say, oh, the most negative value I can store is -8, and then the most positive value I can store is 7. Are we doing okay so far with this discussion? Okay. So now the question is, in general, how do I know what is the largest and the smallest value that I can represent given a certain number of bits? Okay, so that becomes the next question. Yes?
So for when we compare,
Mm-hmm.
and you said, putting a signed variable or a bit to determine whether it's negative or positive doesn't really work when you're comparing.
So we haven't really started to talk about comparing, but in this particular example, the question is, how do you know?
Well, can you just slap a bit on the end of it and then tell whatever the computer is not to count the last bit?
Nope, you do not do that because whether it is supposed to be signed or not is not a part of the explicit representation. The compiler knows it, right? Because when you say int x, the compiler internally keeps track of variable x and say, every time I use x, it is supposed to be signed. So whether it's signed or unsigned makes a difference, the compiler knows which way to crank out the code. Is that okay?
But like the physical.
Exactly. At runtime, that information is not preserved.
An adder wouldn't care whether.
An adder would not care. Exactly. An adder would not care. A subtractor would not care. Yep. But only when you need to compare. And usually a comparison, is it's used in the decision-making process, right? If it is less than, we go this way. If it is not less than, we go the other way. Then, at that point, the compiler knows how to compare so that it knows how to make the decision correctly. Yep. So there are bits and pieces of information in your C source code that is only retained during compilation. The compiled code doesn't have that information, at least not explicit information anymore.
Right. You need an abstraction further.
It's just that it doesn't need to. It doesn't need to carry that information at runtime all the time.
Gotcha.
All right. So getting back to this discussion, how do we get 15? How do we know that 15 is the largest possible value when we have 4 bits? 15, how does 15 relate to 2, which is our base, and 4, which is the number of bits that we're dealing with? Tell me. You guys know the answer already. You just have to kind of formulate your answer. Yep, go ahead. 2 to the 4 minus 1. Yep, I know what you mean. There you go. Very good. What about, 0 is easy, right? 0 is always 0. So for unsigned values, the minimum value is trivial, but the largest value is 2 to the power of number of bits minus 1. Why are we minus 1? Why is 16 not here on the wheel?
You have to carry. You can zero.
Because 0 takes up 1 spot. Because remember, we only got 16 spots, right? If 0 is taking out 1 spot, then the largest integer from the unsigned perspective can only be 15, because if we also include 16, then we would have used 17 spots, which we cannot do given only 4 bits. Okay? So that's why we have a minus 1 here. Okay, what about the signed representation? So I'll just kind of say this is for unsigned. What about for signed? How do we get 7 and negative 8 and 7? Okay, so let's look at the most positive one. 7 is what? 2 to the 3, right? 2 to the power of 3 minus 1. What about negative 8 then? It's 2 to the power of 3. That's right. But what about this? Would anyone object if I say, no, I want to go back to 4. This is just 4 minus 1, and this is just 4 minus 1. Would anyone object to that? I hope not. Okay. Okay, so this is for signed. So now the question is, okay, this is great, okay? We know everything about the range of values when we are given only 4 bits. What if I say I'll give you n bits? I'm not even giving you a concrete number. I'm just saying, okay, assume there are n bits. What would be the largest value for unsigned? What would be the range of values for signed? What do you think? Exactly. So if you have n bits, then for unsigned, it goes from 0 all the way up to 2 to the power of n minus 1. Very good. What about for signed?
Just from 2 to the n minus 1.
2 to the power of n minus 1, and this time the minus 1 is associated with the exponent. And this is negated all the way to 2 to the power of n minus 1, and then minus 1 here. This is why natural language is not very good, because if you say, when you say 2 to the power of n minus 1, there are at least 4 ways to interpret it, right? Let me count. 1, 2, no, there are 3 ways to interpret it. Because this -1 could have been here, and then you can have -1, all not a part of the exponent. So are we good so far with how to calculate the range of values that we can represent given a whatever number of bits to represent things? Yes? Okay, all right. And obviously when n is large, you have a pretty big, number wheel. Okay, so now we move on to something else. We move on to something else that does not seem to have anything to do with a number wheel. So we want to talk about arithmetic negation. Okay, arithmetic negation looks like this. Okay, that's how we represent it in all the math classes. So typically, if x is non-negative, that's the result. Is that okay? All right. So what do we know about negation? Well, we know that if you double negate something, what do we get? We get it back, right? And what if you add the negation of x to x? You get 0, okay. X minus y can also be expressed as x plus the negation of y, right? So we know a few things about negation, as an operator. Now the question is, well, these things are, negation in all of these senses is an arithmetic operation, okay? Because you're flipping the sign, of a particular value, and it's an arithmetic concept. Well, as much as we like arithmetic concepts as a computer science person, we cannot do that using transistors. So we want to find a way to do everything using just transistors. Is that okay? So how do we do that? That's the question. Well, before we do that, we want to kind of observe, a pattern here. Going back to the number wheel. For the left, oh, by the way, this is a good time to explain why I only use assign negative values from -1 all the way to -8 when we only have 4 bits. This way, 1/2 of the wheel are negative and the other half are non-negative. Okay, but there's one more thing. If you look at the most significant bit, everything that can be interpreted negative has a most significant bit of 1. And that bit, the most significant bit, is also known as the sign bit as a result. Okay, so next time, when I say the most significant bit or the sign bit, they are exactly the same thing. Are we doing okay so far? Yep. Okay. So when you look at this number wheel, and also any number wheel, the way we assign the values, the most significant bit, which is the leftmost bit, if the bit pattern can be interpreted as a negative value, then that bit, the most significant bit, is going to be a 1. And as a result, we call this bit the sign bit.
So that's why we call it.
That is why we call it the sign bit, because it indicates whether the number is negative or not. A number is negative if and only if the sign bit is a 1. But that's only if you choose to interpret it as a signed value. Okay, so we look at this and we want to see if there's a pattern, okay? So one little pattern that I can see is 15 minus -1 is 16. 14 minus -2 is 16. 12 minus -4, 16. 10 minus -6, 16. 8 minus -8 is also 16. Okay, well, maybe we can use this, to our advantage. But we actually don't even need to do that. And let me ask you about this. Okay, so we go back to negation here. And we want to say, okay, so here's the equation. 0 minus x, Does anyone want to argue that it is the same thing as 16 minus x plus 16? No arguments, right? Okay. Then can I rewrite it as 16 minus x and then the whole thing plus 16? Of course we can, right? Okay. And then the problem is, well, okay, now at this point we are looking at this and go like, hey, we can do this, right? Because we know how to do a subtraction, we know how to do an addition. But there's a minor problem here. You cannot represent 16 with only 4 bits. Okay? All right. So we can see if we can fix this problem. And you are right, okay? Some of you are already thinking, why don't we just use a subtractor then? We put a 0 up here, and then we put x, as the usual y, and then the result of the subtraction is the negation of x. You're correct about that, but we want to do it as inexpensive as possible. Okay, using a subtractor is not the least expensive way to do this. Yep.
Would it be negative 16 minus x plus 16 equals 0? Minus x.
Say that one more time.
Would it be negative 16 minus x plus 16?
Oh, you're right. Okay. Yep. I goofed. Good job. Yep. I goofed. I goofed up. Okay. Very good. But we still have to deal with 16, okay? So now the question is, if I make this a 15 minus x, and then the whole thing plus 1, and then the whole thing minus 16, we still have 1 minus 16 on the outside. We'll deal with that later, okay? But the 16 in the inside of 16 minus x is now gone. And somebody's going to argue and go like, but you still need a subtractor. Subtractor is still needed. You might as well just use a subtractor to begin with and be done with the whole thing. Well, what if I tell you this? What if I tell you that 15 minus x is tilde x? And tilde x is bitwise not. It's a very inexpensive operation. Now you go like, how does that work, right? So I'll give you an example. So let's take 15 is represented as 1, 1, 1, 1 in base 2, right? Because it's 1 plus 2 plus 4 plus 8. So it's 1, 1, 1, 1. So we'll just do an example here. Let's pick on 0, 0, 1, 0. Okay, this time we are not really concerned about the value it is representing. We just want to know, is it really the same thing as the bitwise not of 2 or 1101? So we'll carry out the subtraction. 1 exclusive OR with 0 is 1. 1 exclusive OR with 1 is 0. 1 exclusive OR with 1 is 1. 1 exclusive OR with 1 is 1. Okay. But what about all the borrows? Okay, let's work out the borrows. So we put a default of 0 here. 1 and 0 is a 0. Excuse me, I take it back. Because with subtraction, you negate the first and the second, right? So we have not 1 and 0, which is 0. Not 1 and 0, which is also 0. 0 or 0 is a 0. Not 1 and 1 is a 0, because not 1 is a 0, 0 and 1 is a 0. 0 and 0 is a 0, so now we have 0 or 0, which is a 0 here. Not 1 and 0 is a 0, not 1 and 0 is a 0, so we have 0 or 0, which is this borrow. And same thing over here, so we end up with an overall borrow of 0. Now, I mean, I can spell out this whole thing, but would anyone complain if I just write that here? Okay. So the bottom line is, when you look at 0010 and you look at 1101, is one the bitwise not of the other? It is. It works out.
If we were to keep the 0, then it would show that it wasn't signed. Or
Which 0? Are you talking about the overall carry? Borrow?
yeah,
Well, the overall borrow does not belong to the result.
So if we put it there, would it make it a positive number when we go to compare it?
But we are only dealing with 4-bit numbers. If you put that 0 in, you would end up with a 5-bit number, which you don't want to deal with.
Okay.
Yeah. So when we deal with subtraction or addition, we fix the width. We only care about, in this case, 4 bits. Is that okay? But how did that work? It has to do with 1 minus 0 is a 1. So you can see how the 0 got flipped into a 1. 1 minus 1 is a 0. You can see how the 1 got flipped into a 0. So the key is whatever you use and whatever you subtract x from has to be a power of 2 minus 1. Because any power of 2 minus 1 in base 2 would be a bunch of 1s. Is that okay? Are we good? All right. What about this minus 16? What if I tell you, forget about that one. Would you buy that? It's like, no, it doesn't make any sense. It doesn't make any sense when you're working with a number line, but it makes sense when you're not working with a number circle. Okay? So let's go back to the number circle. The number circle, in our case, for 4 bits, only has 16 slots, right? We have already established that because 2 to the power of 4 is 16. We only have 16 unique patterns of zeros and ones when you have 4 bits. Okay. To add to something, okay, so let's say this pointer is indicating the current value. To add to that value, we are rotating clockwise. To subtract from that value, we are rotating counterclockwise. Is that okay? So to add to is to rotate clockwise twice by 2 clicks, right? To subtract 3, for instance, is to rotate counterclockwise by 3 clicks. Okay. What happens when you turn by 16 clicks exactly? You have not moved. Let me illustrate. I'm just trying to find a longer object, to do this little experiment. Okay. Has anyone taken a class from Randy Schuster? Professor Schuster has a, I cannot remember the name, but he has a, I think he called it a stick of compassion. It comes from his, he does a judo and stuff like that. So when someone loses concentration, the dojo master will come up with a stick and go like, whack, it's like focus. So, that would be coming in handy now because I need a longer stick to point. But it's okay. Okay, we'll just do it this way. Let's say we're dealing with 3, okay? Here's 3. And I want to subtract 16 from 3. And let's see what happens, right? Subtract 1, subtract 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, 3 minus 16 is 3. Are we buying it? Why not?
If it's a 4-bit number?
It's only if it's a 4-bit number, we can only represent either 0 to 15 or negative 8 to 7. That is your entire range of values. If you try to add any multiple of 16 or subtract any multiple of 16, you get back to where you started off with. This is called modular arithmetic. Okay, everything is basically mod 16. There's a mod 16 after every operation.
So that's why it's a circle.
That's why it's a circle. But it has to be a circle because when you represent an integer in any known programming language, there's only a number of bits that is allocated to the integer. I mean, yes, we can have 64-bit integers, which can represent a huge range of numbers. Well, all that is doing is to make your number wheel really big. So for the most part, you think that you're on a number line, but it is still a number circle. it will come back eventually. Is that okay? Yes?
So is this like a visual representation of like data overflow if you were like trying to do operations?
Yes.
Yeah.
Yes. You can actually observe this in a program. Now, let's see how we can observe this in a program. I'll just write a C program to illustrate this point, because some of you are looking at me and frowning and go like, no, this cannot happen. So nothing says it can happen like a sample program. So we'll just write a sample program. I'll call it circle, okay? So we'll pound include stdint.h. If you have not learned what this is, now is a good time to learn. Standard integer.h is a header file where it predefines, how we can specify an integer that is 16-bit wide, how to specify an integer that's 32-bit wide, and 64-bit wide. Okay, so when you use very specific names, it will tell you what is the width of the integer. Okay, and then we'll write int main, and in here we'll write a loop. Okay, so the way I'm writing this loop is do. So let's do 16-bit numbers. Okay, so I'm gonna have u int 16_t. This is how you spell out a 16-bit unsigned integer as a type once you have pound included standard integer.h. Okay, so in this case, x is guaranteed to be a 16-bit unsigned integer. It won't be 32. It won't be 64-bit. Okay. And here I'm going to say u int underscore t. Oh, it's 32 this time, and this is upper bound, okay, UB. And over here, now with a 16-bit number, what is the largest value I can represent using 16 bits? 2 to the power of 16 minus 1, which is 65,536, I think. Okay. But I cannot represent one more than that, right? But in 32-bit, I can represent just one more than that. Is that okay? So I can spell it out as 65,536, which I think is the correct number, but I'm not 100% sure. Okay, this is why I do not like base 10. If I express it in hexadecimal, how would I represent it in hexadecimal? Remember, in hexadecimal, one digit is representing exactly 4 bits. So how do I specify 16 zeros? When 1 0, huh?
4 digits then?
4 zeros, very good. So if I say that, okay, it is 65,536 as we know it in base 10. Because this 0 is representing 4 bits, 4 bits, 4 bits, 4 bits. So it is 1 followed by 16 zeros in base 2. What is the value? What is the quantity represented by 1 followed by 16 zeros in base 2? 2 to the power of the number of zeros. Oh, 16. 2 to the power of 16. That's just one beyond the largest value that x can represent. Is that okay? Okay. And now I also have another variable, which is my indexing variable, which is I. Okay. So in the actual program, I will give x a particular value. Okay, 3 is fine. You can choose anything you want to. And then we specify a loop. So we say for I, which is a unsigned 32-bit number, equal to 0 to initialize it. I is less than UB, upper bound, plus I. So how many iterations am I going through using this particular for loop? Okay, so am I going through UB number of iterations or UB minus 1 iterations? It's without the minus 1 because I started with 0. In the first iteration, I is 0. In the next iteration, I is 1. So by the time I is this value minus 1, that last iteration would be the 65,536th, iteration. Is that okay? But what do I want to do for each iteration? That's all I want to do. In other words, I'm incrementing x exactly 65,536 times, which is doing the same thing of what I just did using the number wheel, except a whole lot faster and a whole lot bigger, exactly. And then we want to return 0 at the end. And you go like, but this program has no cin, no cout, no printf, no scanf. How does it work? Okay, gcc-g to include debug information, -o, circle, which is the name of the executable, circle.c, which is the name of the source file. Okay, compile just fine. Okay, fine. Some of you are complaining. It's like, aren't you supposed to warn all? Yes. Okay. How many people know how to use a compiler on the command line? Some of you. Great. Okay, I am impressed. All right. So the next thing we do is GDB it. Okay. And how many people know what GDB is and has used GDB to debug programs? 1, 2, 2. Unfortunately, a lot of our classes do not focus on debugging techniques. And as a result, many professors do not teach how to use a debugger. So I'm going to be one of the few to teach you how to use a debugger. This is a command line debugger. It is the back end. It's also in the back end of code blocks. So if you have code blocks, it has GDB capability in the back end already. You can just kind of click on the line to set up a breakpoint. But I don't like to use code blocks. I just use command line tools. So what I'm going to do is I will put a breakpoint at several places. Okay, I'll put one on line 9, and I'll put one on line 12. Okay, so put a breakpoint on line 9, put a breakpoint on line 12, so that I can kind of intercept the program right before it returns. So now I run the program, start from the beginning, single step, okay? And if I print x, obviously it is 3. Are we surprised? No. Okay. We can also print size of x. What do you think it will tell you? X is 16-bit wide. And size of returns the number of bytes. Number of bytes. So what should it return? It should return 2. Let's double check. Okay, so we know the width of the integer is correct now, okay? So C is continue. In other words, when you say continue, it will continue execution until the program exits, it crashes, or it hits a breakpoint, any breakpoint. But the next breakpoint is on the line of the return, which is after the loop, okay? So we press the enter key. Wow, that was fast, right? That's 65,536 iterations right there. It would have taken me a little bit longer using that little pen and a huge, gigantic number circle, right? All right, so this is the moment of truth. What is in X? Well, before we do that, let's find out what is in I first. What do you think should be in I? 65,536. Exactly, it is 36. Because in order to get out of the loop, it has to be greater than or equal to UB, and UB upper bound is 65,536. Okay? But the question is, okay, so let's double check. Yes, okay, that's good. Okay. Now, what is in X?
Wouldn't it be 2?
So, okay, so we got one person saying it's a 2, and do we have any other takers? Huh? It should be 3, okay. Any other takers? -3 maybe? 0? It crashes when I try to print it. Huh?
My overflow?
My overflow, okay. If
Oh,
I
that's
if I
fine.
do a,
Oh, never
when I
mind,
do a
it's free.
when I do this printf, do you think the debugger would say WTF?
No. No, it's gonna be 3 because it's unsigned. If it was signed,
Yep,
it'd overflow.
it is 3. So is this illustrating my point that it is a circle? It is a huge, gigantic circle, but nonetheless, it is a circle. Yep.
Only when it's not signed. If it's signed, it'll overflow.
If it is signed, it is the same thing. It doesn't do a thing. It doesn't make any difference. Okay. So let's go ahead and change the program just a little bit and make x signed. Okay. So now x is a signed 16-bit number, and we'll even change this to a negative value, like -3. Are we good? Okay. So we will recompile the program, run GDB again, and we have the same line numbers, but I forgot already. So we put a breakpoint on line 9, put a breakpoint on line 12, run the program. Now it stops on line 9, single step, print x, it is -3, it's all good. Continue execution, it hits line 12, which means we're out of the loop. Once again, we print I, okay, we print UB, they are the same, kind of makes sense. Print X, it's -3.
Then what's that integer overflow?
Hmm?
It just cleans it with
C doesn't do that.
Oh.
C does,
Oh, this is C.
it will go around the circle, but it won't let you know that you have just gone around the entire circle, which is a problem.
Oh, so C++ will overflow.
Nope, C++ does not overflow either. Neither C nor C++ would care when you cross the border between the largest and the smallest value, signed or unsigned. Let me show you what I mean by that border, okay? When you add 1 to 7 and you cross over to -8 using signed interpretation, you won't feel a thing. Your C++ program doesn't care. It would just go like, well, 0, 1, 1, 1 plus 1 is 1, 0, 0, 0. This is what you're getting. But hold on a second. This is a signed value. We just went from the most positive value to the most negative value. We should know about this. This is bad. The C++ compiler says, nah, it's just a bit pattern. Going from 0, 1, 1, 1, adding 1, using a bitwise operation, bunch of bitwise operations to 1, 0, 0, 0. It would just go like, so what? Okay, that's one border. Okay, if you're dealing with signed values, this is one place you should not cross over. Yes?
Does it corrupt the neighboring bits? Or does
Huh?
it know not? Does it corrupt the neighboring
Nope.
bits? Or
There are no neighboring bits to corrupt unless you use that integer as an index. Then bad things will happen. Okay? The other border that it should never cross over is over here. Because if you add 1 to 15, it becomes 0 when we are talking about 4-bit integers. Okay? It does not make sense. But the compiler doesn't care. The compiler will not crank out any code to detect you go from here to here or you go from here to here. Question?
It only corrupt or overflow if you're using it as an index because it takes up another spot in memory.
Because if you use it as an index, okay, so let's say we are using unsigned integer I as an index inside the square bracket, right? Okay. And you are decrementing in terms of the index because you're going backwards in an array, okay? So you go like, okay, we're looking at element 3, element 2, element 1, element 0, and now you're looking at element 15. Does element 15 exist? Probably not. But your C code does not know that it does not exist. So it will pretend as if element 15 does exist. And if it did exist, it would have been that location. And it would have just used a location to say, okay, you want element 15 of this array? Here it is. Okay. In my cisp310 class, I made an analogy of what C is really like as a tool. Okay, it's a tool that was made, designed and originally made by two programming gurus. Okay, these people were writing the Unix operating system in the 70s, and they were trying to write the entire thing using assembly language, it's not like they could not do it, but it is very time consuming. There's a lot of chore. So this guy just decided to go like, okay, I'll just make a tool to make my job easier. That tool was known as B or BCPL, which later on became C. So you're looking at a master carpenter saying, oh, this is, chopping these wood, is taking too much time. I need a circular saw. Instead of going out to buy one and have someone to design one, something that has all the approval from all the safety agencies, this guy just looking around, go like, okay, there's a half horsepower electric motor here, great. Oh, there's another saw blade over there, great. Weld it together. Here's my circular saw. How do you turn it on? What do you mean by how to turn it on? Just plug it in. Then how do you line up things? What do you mean by? Just hold on to the motor, okay, and be very careful and cut your wood. What is your problem? Next day, you guys came in as CISP students, right, or CISP 360 students. You are the apprentice to the carpenter. The carpenter hands you exactly the same tool and go like, okay, as your first exercise, I want you to cut up those 4x8 sheets into cut one into 4, okay? And by the way, watch your fingers. That's C and C++. So you guys all survived CISP 360 with all your fingers intact, right? Maybe. So as we get through this class, you will see why C and C++ is good in a way, but also bad in a way, okay? Because we'll start to translate C code into assembly code at the lowest possible level. So that will give you an insight of what is really happening when you say, okay, here's an array of 4 elements, but I want to get the 8th one. What is going to happen? Okay? Now, if you're just reading the 8th element when you only get 4, well, okay, you're reading some garbage. Okay, we really should not be using it, right? But what if you're overwriting that location? Then you're overwriting some location in memory that does not belong to you, and depending on who owns that location and how it is used, your program can have very weird symptoms. Okay, main calls G, but G returns to F, which you never called. That can actually happen. Or you call a subroutine, it returns, but it doesn't return back to where you called it. It returns to a much later point or to an earlier point. All of that can happen when you access an array out of bound in a very innocent way. Okay, so we'll see all of that later on. But to answer your question, C does not care when you cross over from 7 to -8 for signed values. It does not care when you cross over from 15 to 0 for a signed 4-bit number. So you have to watch out for those conditions. You have to know what range of values you need to work with and then use the correct width of integers accordingly. And that is also why you have to use standard int.h so that you have 100% control over, am I talking about an 8-bit? Am I talking about 16-bit, 32, or 64-bit integer? Because you should know what range of values you need to work with and then use the correct width when you choose the integer types.
So what's the difference in saying like int? It's like,
When you just say int,
yeah.
okay, so when you just say int, it depends on what platform you're on, okay? Now, this computer is running a 64-bit version of Linux, so when I say int, GCC says, oh, natively an int is 64-bit, so int is going to be exactly the same as int64_t. The same program, the same C program, if I go to an earlier version of Linux, which is 32-bit, okay, and I run the same GCC, same version of GCC, it will say, oh, int is natively 32-bit. It will give me a 32-bit integer instead, okay? Now, even better, if I take the same program and go to an Arduino platform, okay, Arduinos run on the Atmel 80 mega platform, which inherently is an 8-bit processor. but int is actually 16-bit natively. So now, if your original program running on a 64-bit platform can run to a range of, let's say, 100,000, okay? 100,000 is not a problem with a 64-bit integer, not even breaking a sweat, okay? It's all good. You move on and port it to a 32-bit platform, well, it's okay, because 32-bit can handle up to -2 billion to +2 billion, okay? So 100,000 is also not a problem. And then you port it to a 16-bit platform. Unfortunately, on a 16-bit platform, even if it is unsigned, it only goes from 0 to 65,535. So your program will not work when it exceeds that range. Now, how your program breaks, when it breaks, it all depends on what condition will cause that integer to overflow from 65,535 to 0. It becomes very difficult to debug that program because it all depends on what it is dealing with, just because sometimes you will reach 100,000 doesn't mean it happens all the time. Am I kind of making the point? Okay. So this is something that professional programmers always consider is, okay, I have an index variable here, or I have a variable to hold the result of a calculation. What range of values am I dealing with here? What is the minimum? What is the maximum? And then you have to choose the correct type of integers accordingly. Okay. For most of your classes here, it is probably not a concern because you don't have to cross platforms. Okay, it's not like you write something on the 64-bit platform and then later on you have to port it to a 16-bit platform. But in industry, it happens all the time. Because most of the things, like a Fitbit, okay, it probably has a 8 or 16-bit processor. So you develop some of the code on a larger 64-bit platform because it's easier to debug and check the logic. You port that code onto a 16 or cross-compile the code to a 16-bit platform, and it suddenly doesn't work. Well, it can be because of the range issue. So issues that are not exactly related to assembly, but it is low level enough that we should talk about it in this class. Any other questions? I cannot remember where we were. Yep.
That has to do with, how in 32-bit processor you can only use up to 4 gigs of RAM. Is that something that has to do with that?
Okay, so the address space of a 32-bit architecture is usually also only 32-bit wide. So that means you can only have memory locations from 0 to 4 billion something. So that is one, okay? But the issue of your platform dependent width of a default integer width has to do with the compiler is thinking, okay, so natively on the 32-bit processor, it will only take 1 clock to do one addition. But if I want to do a 64-bit addition, it will take 2 clocks. So why do I want to make that preparation when the processor only natively can handle 32-bit? So the GCC compiler on the 32-bit platform would natively assume and say, if you just say int, I'll give you 32-bit, because it makes sense on that particular platform. When you're on a 64-bit platform, it doesn't make sense to default to 32-bit anymore, because it will take 1 clock either way. Okay, to add 2 64-bit numbers, it will take 1 clock. To add 2 32-bit numbers, it will take 1 clock. To add 2 16-bit numbers, it will take only 1 clock. It doesn't make sense to default to a smaller width on a 64-bit platform. So that's why the default width of an int depends on what processor are you talking about. Okay? And as a result, if you design any code that has to cross-platform, then this issue that we have just been talking about becomes a major issue. Because you might be writing code here, and then later on decides to port the code to somewhere else, and then it stops working if you do not take care of this potential issue. So from all this discussion, do you think I have been bitten by that bug before? Yes. Yeah. There's no such thing as wisdom. It is only how many mistakes have you made, and did you learn from those mistakes? So if you lose a finger, you say, how do I preserve the other 9? Then you might have a better chance of preserving the other 9. But if you lose one finger and you do not think about how to preserve the other 9, then you're down to 8, 7, and so on. All right, so do we have any other questions? We're kind of running out of time. So I got one last, yes, go ahead.
So on the transition from 15 to 0, unless you allow a 5th bit to take that carryover, that is just lost.
It is just lost. The carry bit, the overall carry, is not a part of the representation of the integer. So when you say 4-bit integer, it really literally means every integer only has 4 bits. Now, does it mean the overall carry or the overall borrow is not useful? No, I did not say that. Okay? It is still useful for certain things, but it is not stored as a part of the result. And that is why when you add 16 to 3, it is just 3 when you're dealing with 4-bit numbers. So are we good so far with all this stuff? Yes? Okay. So let's go ahead. We got 2 minutes left, so I got one more extra thing to tell you. You guys might have heard, pearls of wisdom, right? How many people have heard of that phrase? Okay, comparing wisdom to pearl. Well, it is actually very accurate because do you know how pearls are actually made? It starts as irritation, like sand that got trapped in a, not oyster, but any type of those animals. Oysters is one of them, right? So what does oyster do when there's a piece of sand or irritant getting into its, system? It surrounds it until it's not irritating anymore. So pearls, comparing to wisdom, is the same way. Wisdom is works exactly the same way. You make a mistake, you go like, ouch, that hurts, right? So what you do is you learn from it and go like, okay, if I learn from this, hopefully it won't hurt me in the future. So wisdom is formed exactly the same way as pearl. It starts off as irritation. So when you say, oh, Tag, you have so many pearls of wisdom, it is not a compliment. It just means that I have had a lot of irritations. Okay, so we're going to transition to the lab in a few minutes. The lab is already open. So I will see you guys over there as I shut down the computer here. And by the way, I do not have any pearls of wisdom.